Thanks very much. Good afternoon. Thanks especially for the flawless pronunciation of my surname. So I tried to recap the most important parts of what was in the lecture this morning. That should be over here, basically. There's two main theorems, the KKL, BKS. KKL stands for Kahn, Calais, and Lineal. BKS stands for Benjamini, Calais, and Schramm. These are fundamental theorems. None of them have been proven yet in the lectures, but they are things you should keep in mind during the exercises. You should also keep in mind the obvious basic definitions, what a pivotal bit is, what influence and total influence is. I'm also going to use the notation of, I don't know if this is the letter, if this is the Roman numeral 2 or if it's the capital letter pi, but that's how I'm going to denote the sum of the squares of the influences. And you should recall what it means to be noise sensitive and noise stable. You should recall that these are essentially each other's opposites, but that there's a whole spectrum of whatever may be in between them. So this is not the full picture, so to say. Okay, there we go. You can reach me at frej@chalmers.se if you have any questions about anything. I'll try to put solutions up online at some point in the future, perhaps after the course, but not ready now. Okay, so let's start with exercise 1. That's a pretty easy one just to get warmed up. So we want to determine the pivotal set, or actually, I mean, you have to determine the pivotal set to even start determining the influence vector of your first examples. And our first examples are, I'll do all of them at sort of once. The dictator function. Recall that one takes a long string of bits omega and just returns the first bit. The second one was parity, which takes a string of bits and outputs their product. So it outputs a 1 if there's an even number of minus signs in the string, and it outputs a -1 if there's an odd number of them. The third example is majority, which takes omega, gives you the sign of the sum of the bits in your string, and for simplicity, I guess we suppose n is odd. Otherwise, it won't make a big difference, but there will come more examples. I'll do 2 more examples afterwards, but let's keep to the simple ones on the board for starters. Okay, so what's the influence vector of dictator? This is basically just to make sure we understand what an influence is. Okay, so for the dictator function, the output is determined by the first bit, obviously. What does that mean? Well, that means if you flip any other bits but the first one, nothing will change. On the other hand, if you flip the first bit, the output certainly will change, okay? So for dictator function, the first bit is always pivotal. While no other bit ever is. Okay. Was there anybody who didn't follow what I was saying? So try to make sure from the beginning. Okay. So hence, of course, the influence of the first bit is going to be 1, while the influence of all the other bits is going to be 0. Okay. Second example, parity function. Okay, so what about parity function? So I give you an input, omega. This produces an output, which is just the product of the bits. Now, if I flip any one of the bits, I flip any plus to a minus or a minus to a plus, well, of course, that's going to change the parity, right? The product is going to change because I'm going to multiply by a minus sign. So whatever input I do and whatever bit I flip, I will always change the output. So for parity, every bit is always pivotal. So all the influences are equal to 1. Okay. So these are, in some sense, the two extreme cases. Because for the dictator, we obviously get the total influence obviously equal to 1 plus a lot of zeros. So the total influence is going to be 1. Whereas for the parity function, the total influence is going to be n. And it's pretty clear that this is the spectrum we're going to have. I mean, we can never have a smaller total influence than 1 and never a larger one than n. Okay, so these are, in a sense, the extreme cases. Now, the dictator may not be a very natural function. I mean, it may be a natural function to look at, but usually too silly to even consider a function. So in another sense, I would say an extreme case, if we only look at transitive functions, that's a very natural class of functions. That's essentially the functions where every bit plays the same role. Okay. Among these, there's another extreme case. That's the one I've already written down there. That's majority. So what about majority? When is a bit pivotal? I give you an input, and I point at the bit. OK, so everybody has voted. What's the probability? In which case is the 19th voter pivotal? In which case can he himself determine the outcome by flipping his vote? Well, for the majority function, I is pivotal if and only if, well, he should determine the sign of the sum. That means that all the rest of them should not be able to decide on the sum. So the sum of all the other bits, must be equal to 0. So what's the probability that the ith bit is pivotal? That's going to be, well, obviously the probability that a sum of n minus 1 things, n minus 1 plus minus 1 variables, the sum should be equals 0. Now what's the probability that happens? Well, that happens with probability, as you can easily check. Let's see here. N minus 1, choose n minus 1 halves divided by 2 to the n minus 1. Right. So this is just the size of the outcome space, and this is the way to choose the plus voters and the minus voters, respectively. And of course, this is easy to see that it behaves something like a constant over square root of n. Okay, so So Christoph hinted at this already in his lecture that, okay, he said that this could be taken as a sort of proof that the influences can be reasonably small. I mean, it's certainly far smaller than constant, as we have in the parity case. But on the other hand, we shall also see that it really is quite extreme in the sense that this is an extraordinarily, for a transitive function, an extraordinarily big influence. So was there any question on these first warm-up examples? I'm going to continue then by looking at the iterated majority and at the tribes example. And these are slightly harder, so I've given you time to think about them. And actually, they're harder to write down too, so I'm gonna need to erase them. Our fourth example is iterated 3 majority. If you don't remember, that's the function where I should elect a president, and then he's elected by some representatives that are right behind him, below him, who in their turn are elected by representatives, blah, blah, blah. If you want to see it differently, this is like the result of the outcome of a tennis game, which is determined on who wins the most sets, which is in turn determined of who wins the most games, which is in turn determined by who wins the most balls, etc. So how this is defined is if you, for example, have a majority of pluses there, you get a plus there, and then perhaps this one is also a plus, and then the top guy is determined to be a plus. Okay, so look at this for a minute, and then try to determine the influence vector of that. I'll write down the tribes example, but I'll discuss it later. So does anybody have an idea on what's the influence, if we don't know anything about the outputs anywhere, what's the influence of this lad? Anybody? Well, for starters, obviously, I said you should determine the influence vector, but obviously this is a transitive function because, I mean, the bits all play the same role. So it's enough to determine this influence. Yes, Balázs? Right, so this is level k. K is the height of the tree, right. You said 2 to the minus k. It's totally right. Would you motivate it?
Well, for k equals 1, it's quite obvious.
Right.
And then you observe that if you look at the entries, so what you see on the top of the little tree of 3 leaves, then on the top you see again a fact point plus. So it is okay. So
Perfect. That's exactly the argument, right? So for this lad to be influential, to be pivotal, it has to happen that, okay, so in the first place, this one mustn't know what sign it has before it has asked him. So it must be the case that these two are 1 plus and 1 minus. Okay, this happens with probability half. Now, given that we know that, everything that happens over here is still independent of that. Okay, now it also must happen that, for this one to be influential, that this one doesn't know his outcome after having asked these two. So these two have to have different values, which happen with probability 1/2 independently of what happened in this subtree, and so on. So by induction, in the fourth example, every bit has influence 2 to the minus k, which is, if you maybe want to, I mean, let's be happy about that, but sometimes maybe you would like to have it described in terms of the number of variables, but then you have to have some logarithm yoga, and you all can do that for sure. I mean, if I would like to write it as a power of n. Okay, that's very good. So the more tricky example, not horribly tricky, but I mean, something new, the tribes example. So Christoph mentioned it as the extreme case for having very small influences. Now we're going to show why it really has that small influences. So remember, the example is you put all your bits on a line. You look at the first log n minus log n ones. All my logs are always base 2 for simplicity. And then you group them into blocks. Each has length log n minus log n. And of course, you might squeeze in, if you would like to, you could squeeze in n over log n minus log n blocks. Actually, for the calculations, it gets easier if I'm happy with only squeezing in n over log n blocks and then leaving all the other bits there at the end as some sort of debris, something we don't care about. This won't make a difference for the influences, really. I mean, not for the order of the influences. So what's the influence in this example? Oh, sorry, I didn't tell you what the function was, perhaps. Okay, so if there is some block in which all the bits are 1, then the function is 1. Okay, so tribes equals 1 if there is some block where all bits have plus spin and it's 0 otherwise. What does it take for a bit to be pivotal in this case?
Every block except for the one that's in has to not have all pluses, and its own block has to have all pluses except for the
Certainly. So this guy is pivotal if it is the case that all the other guys in his block are plus ones, and all the other blocks has some minus sign somewhere in them. Okay. So what's the probability of this happening? The probability of of any guy being pivotal is the probability of this thing happening. Now, notice that the bits are independent, so certainly what happens within each of the blocks is independent, and this is crucial for the analysis. So what happens in this block is independent from what happens in this block. So the probability factors like this. The probability of this thing happening, that's obviously 1 over 2 to the log n minus log n minus 1, I guess. And the probability for this thing happening is, right, this is essentially the same thing as saying that the tribes function does not happen. Essentially, it's the same thing. For simplicity, I will actually write this as 1 minus the probability of tribes. You should notice that there's some subtleties which you don't really have to care about because there's too few blocks. I mean, there's one too few blocks here for this to be exactly 1 minus p tribes, but that's obviously ignorable. Now, 2 to the log n minus log n is obviously, or once you do some thinking about it, it's log n over n. And then we had a minus 1, so we get a constant 2 in front. OK. So this is certainly less than or equal to a constant times log n over n. OK. So it actually matches up to a multiplicative constant. It matches the lower bound, the extreme case claimed by KKL. Yes?
Is the constant sharp in the KKL theorem, or it's not the same?
It's not the same. It's not the same. So, I mean, you can probably, I mean, being careful about what logarithms, no. Being careful about the exact sizes here can, of course, improve the constant, and being careful when reading the proof will give you, can improve the constant. I still don't, they're not horribly far apart, but there's probably a factor 10 or so missing. Yeah. We're really interested in asymptotics about these things anyways, but it's a good question though. It would, of course, be interesting to see what's the very most extreme transitive function in this case. OK, so if we really wanted to know what the influence vector was, then we should know what the probability of tribes is, of course, because maybe this thing would drift up to 0, in which case we would get something even smaller. OK. But that's what we're going to do next, in fact. So I'm going to show you, the question is, or you're going to show me rather, that the probability of this, or the expectation of this tribes function is bounded away from 0 and 1. Or in other words, that the variance of the tribes function is bounded away from 0. Actually, this is not going to be too interesting. This is, to a large extent, going to be calculations of the kind I've already shown you. But, yeah, so how do we calculate this? The easiest way is probably to calculate the probability of the complement, right? So the 1 minus 1 minus probability of tribes occurring. That's just the probability that in not all of the blocks there's some minus sign somewhere. So it's the probability that a block has a minus sign to it that each of the blocks does. So that's the probability that a particular block has a minus sign in it to the power of the number of blocks, which was n over log n. Right? Now, of course, this thing happens with probability. The probability that there's some minus sign, that's of course 1 minus the probability that there's no minus sign, which we just recently showed had probability log n over n. Okay. So if you're unsure about this, I might repeat once again that it's really 1 over 2 to the log n minus log n, which when you calculate it turns out to be log n over n. Raised to the power of n over log n, blah, blah, blah. This n goes to infinity, then n over log n obviously goes to infinity too. And this is going to behave like 1 minus 1 over x to the x. X goes to infinity. We're going to get something that converges to 1 over epsilon, 1 over natural basis of logarithm. Okay. So indeed, the probability of the tribes function goes to something non-trivial.
Excuse me, why the number of blocks is n over log n?
So I said so we really could, if we wanted to, we could have n over log n minus log n here, right? Because each of the blocks had log n minus log n bits in them. Okay.
It's an approximation.
Yeah. It's, I mean, rounded upwards or downwards or whatever. I mean, this will not matter. So all my logarithms will be base 2, and when I divide by something, then I'll probably round it to an integer for simplicity. Okay, so that's curious. That's not so curious as this thing, perhaps. So we saw here that we could get an influence that's as small as log n over n, essentially. An influence small as log n over n, essentially. But that was because we got something like, writing this out for the third time now, 1 over 2 to the log n minus log n. Wouldn't it be better to just, if I could get this away, then I could just have 1 over n down there. This would give me an even smaller influence, right? It would. So it's kind of natural. Why didn't we instead look at much more natural function that divides all our bits into blocks of size log n? We would still get n over log n blocks, and we would get a new function with only very slightly larger blocks, and apparently it seems like influences would be 1 over n. What goes wrong? Perfect. So at a very naive site, it might look like this would contradict KKL, but it doesn't, right? Because we're gonna be off by the probability of the function will not stay away from 0 and 1. In fact, it doesn't look like such a big restriction that we ask that another log n bits should be 1, but it really is. Okay, so notice that what we would get for this version of the function, let's call it tribes prime. What we would get for that one would be influence of a bit by exactly the same argument as here. We wouldn't get 2 log n over n, but rather 2 over n times 1 minus p tribes prime. Okay, so far so good, but what we're having over here in the KKL theorem, we're not having 1 minus p, we're having variance here. So variance can of course be written as the p of, having a function here, okay. P of f means f is, probability f is 1. 1 minus p of f. Okay, so what we're lacking in order to contradict the KKL example is this pf there, which in fact is going to kill it. Okay, that's very good. Any questions so far? Might go into a bit more other stuff. Exercise 4 is about a geometric interpretation of the total influence. It's not so hard, so it's really more of an observation than an exercise. But I think it's good to use this first exercise session to point out some things that are fairly obvious, but that maybe you wouldn't think about if they were not pointed out. I can erase this, right? So we've got our space, probability space omega n, which is just the outcome space omega n is just plus minus 1 to the n. This can easily be endowed with a graph structure. And the graph structure is nothing but the graph of the hypercube. The hypercube is famous for looking something like this. It's also the only polytope I can draw convincingly, I think. So 0, 0, 0. Let's see, 1, 0, 0 perhaps. 1, 0, 1, 1, 1, 0. Well, I mean, you get the point here. 0, 11, 11, 0, 1, 1, 1. Okay. So it has a natural graph structure where 2 outcomes are adjacent if there's exactly 1 bit flipped to get from one to the other. Oh, think plus and minus instead of 0 and 1, obviously. And then, of course, a Boolean function can naturally be identified with a subset of the vertex set of this graph. For example, this subset, for example, corresponds to the majority function, right? The elements which have a positive, which has more ones than zeros. Okay, but with this picture in mind, there are some interesting things to draw, namely a bunch of edges like this. Did I miss anything? Yeah, that one I missed. So these are the edges that go from an outcome from a red outcome to a white outcome. So from some place where the function is 1 to some place where the function is not 1, where it's 0. So the yellow thing I drew is generally called the graph boundary, the edge boundary in the graph of of the set A, where the set A is the red set. We continue honoring the soccer champions by our choice of colors here. Okay. So now I claim that, in fact, there's a geometric way to look at the total influence of a function, namely as the size of the graph of the edge boundary of the corresponding set. I mean, I'm all the time changing between sets and Boolean functions. I hope you don't bother. I hope you don't mind. And we divide by 2 to the n minus 1. Okay, so here's another way of, that's another way of looking at the same thing. Now, why is that true? I claim that this is true. Why is it so? Well, in fact, the total influence is, by definition, it's the sum over all the bits, the probability that f of omega I is not equal to f of omega. What's the probability? What's this probability? That's just, of course, sorry, sum over I. That's what I was supposed to write. Well, it's just the probability that a given edge in the ith direction is pivotal. The pivotal edges are obviously the yellow things. So the number of pivotal edges, the number of yellow edges in direction I divided by the number of edges in direction I altogether. The number of edges in direction I is obviously 2 to the n minus 1. So what is this? This is just 1 over 2 to the n minus 1. And we sum over all I the number of yellow edges in direction I. So all we get is the number of pivotal edges, which is exactly what I have here, namely the edge boundary of f. Okay. So there's a transition between a sort of probabilistic viewpoint and a combinatorial geometric viewpoint on the same thing. This is going to come in handy at points in the future. Okay.
So can you say again what is this formula?
What is this?
So this is the same formula?
This is
the Russo formula?
no, it's not. No, it's not. This thing, or
What did you prove?
what I proved is that the total influence, the sum of the influences, equals the fraction of equals exactly the size of the edge boundary of the corresponding set divided by 2 to the n minus 1. Okay. So this is essentially, in total, there are n times 2 to the n minus 1 edges in this graph. So essentially this, on the right-hand side, is just n times the fraction of edges that are pivotal. Okay. Was that answered your question to a reasonable extent? Okay, thank you. So now let's transfer from the easy to the not quite so easy. I want you to prove that the variance Okay, so I'm looking at Boolean functions over here. Oh, am I looking at? Yeah, I'm looking at functions into plus and minus 1. Prove that. If f maps omega n to plus and minus 1, then we have the variance of f is bounded by the total influence of f. In fact, it's bounded by 2 times the total influence of f. But the interesting thing here is obviously that there's some constant, but this constant is obviously also going to change if we replace plus minus 1 by 0 and 1. So don't worry about the exact constant, but it's about bounding the variance in terms of the total influence. Now, this is rather natural to think that something like this might hold, that the variance can't reasonably be bigger than the actual, than is allowed by flipping the edges, because if it varies very much, then there must be a reasonable amount of edges that change the outcome. There's a hint given in the exercises. It says something like, okay, express this variance in terms of f of omega and f of omega bar, where omega and omega bar are independent with the same distribution. And once you have done that, try to interpolate between omega and omega bar. This is a hint. I'm not sure if it's a useful one, but you can have it as some place to start thinking while I erase the board. Sorry? Sorry? So this thing, the total influence is just the sum of the influences of the...
No, I'm saying the 2 is not there.
The 2 is not there. Yeah, no, no, it's not there, but it's... It's quite right. I think it should be there, but let's see when we carry it out. If I map into 0, 1 there, if I map into 0, 1, I even claim that there would be a half there, which would be even better. So yeah, probably that's why. Okay, so that's certainly why. If it doesn't say in the notes explicitly that we map to plus minus 1. Oh. Great, so I think this, often it's preferable to map into 0, 1 because then you think of it as an indicator function, but quite often also I think it's preferable to have a variant, that the functions should have second moment 1, because then calculations become easier. So that's why I choose to map to plus minus 1 here. Thank you. Okay, so for starters, do you want me to prove this? This is just yoga using your standard definition of the variance and then a few lines. Well, I guess half a line on this blackboard. If we just assume that this is true, then the interesting part is in what follows from there. And if you're unsure about this thing, then let's just discuss it afterwards. Does anybody have an idea on how to sort of interpolate between omega and omega bar?
Take a function that's equal to omega up to index I and then omega.
Brilliant. So define omega I equals omega I in the sense that the jth index is, let's see, it's the jth index of omega if perhaps j is less than or equal to I, and otherwise it's the jth index of omega bar. That's something like what you intended, right? Okay, and then, of course, we have omega naught is going to be constantly omega bar. And omega n is going to be equal to omega. Okay, brilliant. Now, if it holds that f of omega, if this thing on the right-hand side here occurs, if f of omega is different from f of omega bar, then we're certainly going to have f of omega. Then that means that f of omega naught is different from f of omega n. So it means that f of omega I shall be different from f of omega I plus 1 for some value of I. Okay. But note that every omega, each of the omega I will be uniform on the omega n, on the hypercube. The omega I are, of course, not going to be independent, but each of them is going to be uniform on the hypercube. So this means that, so what does this mean? Okay, if f of omega I is different from f of omega I plus 1, that certainly means that, well, these two sequences are the same except in the ith position, or I plus first. These things always confuse me. Okay, anyway, they're equal in all but one position. Okay, so what we get from this is the probability that f omega different from f omega bar, that's less than or equal to the sum over I probability that f of omega I is different from f of omega I plus 1. Simply by the union bound, right? If this happens, then some of these events, then at least one of these events must happen. Okay. But the sum over, but the since omega I is uniform, this probability is just equal to, by definition, the ith influence of the function f. Because the ith bit I'm thinking it's I plus 1, right? The I plus first bit is flipped when going from here to here. Okay, but this is just the sum of influences, which is, by definition, the total influence of F. Right. So do you have any questions there?
So what is omega bar?
Omega bar is another uniformly chosen string of bits, which is chosen independently of omega. So what I do is I write the variance as 2 times the probability that the function value changes when I take 2 independent bits on my hypercube. And what I do is I kind of walk.
So I is going to be the first different digit between the two?
I is going to be, no, so what I'm doing here is I'm walking from this one to this one, from between my 2 bits, and I'm flipping the first bit. Maybe I don't need to flip the first bit. Then I'm flipping the second bit if I have to, and so on. And at least at one point I have to have flipped the function value. So I'm summing over I, but I'm using the union bound here, so I'm not looking at which is the first place where the function flips. I'm just saying that it flips at one point. Okay.
When you pass the probabilities to the influences, you miss the factor 2.
You think so?
Yeah, because the influence is the number of points where you can change, but there you have the probability that F comes.
Yes. Okay, I see. Yeah. Okay, you're totally right. Thank you. So right, because with probability 1/2, these two will be different, and once we know that, with the influences, right. So what we get here, I suppose we get 1/2 in front like that, right? Brilliant, and then we actually get. This only improves the constant to 1 there. Thank you. Problem resolved. I'm not bringing any own candy here, but there's some leftover if you want afterwards. No. Okay, any other? I'll save them, promise. Any other questions, comments? I'm going to the sixth question then, at least according to my notes. Let's see if I can find it too. Oh, I should prove that majority is noise stable. That's my next mission. If you don't mind, I'm going to wave my hands a bit here because so I don't run over time and so that I have time to do some more interesting question. I'm happy to show you afterwards by the pool how to do the details here. Okay, so majority is noise stable. That's what I claim. So to show that, I need to prove by definition that the probability that the majority on the votes is different from the majority on the noised version of the votes tends to 0 with epsilon? Well, of course it does. I need to show that it does so uniformly in n. That's the critical point.
Sorry, but it's the definition of noise sensitive and stable. What's for every epsilon, there's this and epsilon.
Okay, so good that you asked because it's quite crucial. So for noise stable, it means that as epsilon goes to 0, not only should the probability that we flip the value go to 0, which of course it does, it should do so uniformly in n. Okay, so this is a matter of convergence in epsilon, whereas noise sensitivity, this is really something that for all epsilon. So it's kind of the roles of n and epsilon are kind of flipped here. So for all epsilon, the covariance should tend to 0 with n. Okay, so that's important to point out. And this already, I mean, that the fact that the definitions look so unsimilar in a sense should hint that it's these are really only correspond to the extreme cases. Okay, so what I need to show here. So the very first naive approach is to say that, okay, maybe, I only flip an epsilon portion. Maybe I don't even flip enough bits to change the majority, to be able to change the majority. Well, that's false. That's obviously false. Because look at this. We're going to have a here I point out the votes of the American jury, and I place it. And this is typically, I'm counting the number of votes for Al Gore here, and it's typically going to end up somewhere around, roughly about n½ plus square root of n, something like that. Now I'm going to flip an epsilon portion of the bits. So I'm going to flip something like epsilon times n bits. So I'm certainly flipping enough that we potentially could get over from here to the other side. But what I'm typically going to do, of course, is I'm going to flip a bunch of guys to the right and a bunch of guys to the left. Each of these are, it's going to be slightly biased to be flipped to the left if I ended up on the right and vice versa, but not so much. So the moral of the story is that the sum of the bits, maybe it's better to do it this way. The bits really are plus ones and minus ones. So the sum of the bits is going to be something roughly like, it's going to be order of square root of n. And then the sum of the flips. By what do I mean by the flips? I mean xi, epsilon minus xi. So this is 0 in most cases, and it's +1 if I go to, it's +2 if I go from -1 to 1, and it's -2 if I go from 1 to -1. Well, this is going to be, each of these guys are going to have a mean of roughly epsilon. And I'm going to sum them up, so I'm going to get something that's roughly square root epsilon n. So if you want to look at it that way, I'm going to flip roughly epsilon n bits, and and the overweight in one direction or the other is going to be roughly square root epsilon times n. So this is not going to be enough to actually carry me from, if I've already won by roughly square root n, I'm not going to flip enough bits to go back to the other side. That's the moral. Basically how you prove it is you need to do something like the following. The probability that majority at omega is different from majority at the noised version, that this event is contained in the event that either the sum of the bits in the first place was either exceptionally small, for example, epsilon to the 1/4 times square root n. Remember, this thing would typically be square root n, so having it as small as epsilon to the minus epsilon to the 1/4 times square root n would be exceptional. And then either this happens, or we really flipped a lot of bits, or really flipped exceptionally many bits. So the sum of the xi's minus the xi epsilon is larger than epsilon to the 1/4 times square root n. Now, once again, this thing is basically going to be something like epsilon to the 1/2 times square root n. So this is, now we really flipped a lot if this occurs. So now we only need to show that each of these events, each of these probabilities go to 0 uniformly in n. That's not so hard to show using the central limit theorem, for example, and you don't even need to estimate anything. You can basically use only standard things about convergence. Right. So if you're unsure about how to do this, please feel free to ask me afterwards. Comments? Questions? I would like to do something about proving noise sensitivity in two different ways for so now obviously we know that dictatorship is noise stable. You hear that, I mean, you understand that from the beginning. It's very stable. That parity is obviously very, very noise sensitive, because as soon as you start flipping bits, you're going to go to and fro between plus and minus 1. And we've shown that majority is noise stable, which was the first non-trivial thing we showed. I would like to show one non-trivial noise sensitivity too. So I'm going to show you that, or hint for you why the iterated 3 majority function is noise sensitive. I'm going to show you in 2 different ways, if I have time. Of course, we have a very nice theorem out on our right-hand side from Benjamini, Calais, and Schramm, saying that if the sum of the squared influences tends to 0, then the function is going to be noise sensitive. I should mention a few words about this theorem. The converse of this is not true, as is easily seen, because if you take fn to be parity function, for example, parity function clearly is noise sensitive, but it certainly has influences which are very, very large. And overall, you should think that this theorem is kind of mysterious, because you would think that, in general, functions with high influence should maybe be more noise sensitive, because if you're likely to flip the value when flipping a bit, well, that probably should mean it's kind of sensitive. Okay. Now that intuition only holds to some extent, but parity shows that it holds to at least some extent. So the converse is not true. The converse is true for monotone functions, but that's not the main point. For monotone functions, the converse will, on Monday or so, you would consider that the converse a triviality for monotone functions. So the interesting part is really this direction. So we should show that 3MA is noise sensitive, and let's try with BKS. Well, as we already showed in the beginning, we know that the influence of the ith bit of the iterated 3 majority on k levels is 1 over 2 to the k. So the sum of the squared influences of this function is, well, each squared influence is, of course, 1 over 2 to the 2k. And what's the number of bits? Well, the number of bits is 3 to the power of k, right? Because we have a ternary tree on k levels. So this is just 3 to the k over 4 to the k, which clearly goes to 0 as k goes to infinity. By BKS, 3 majority is noise sensitive. Now you can react in 2 ways to this statement. The first way is to say, wow, so BKS really is quite a powerful theorem, eh? And that's true. And the other reaction is that that's kind of cheating because we didn't prove the BKS yet. So I would like to hint to you a way to prove this without using the BKS. So we need to show that the probability, to show noise sensitivity, we need to show that the probability of that the function in omega equals the function in omega epsilon minus would you bear with me if I say that what we need to show is that this probability is a quarter? We want to show that these 2 events, probability that f of omega is 1 and f of omega epsilon is 1, that these are asymptotically independent. But each of them clearly occurs with probability 1/2 because the function is symmetric between the pluses and the minuses. So we need to show that this probability is a quarter. It tends to a quarter, obviously. Sorry, was that what you asked? Or was there any other?
For fixed epsilon,
Right, of course. Sorry. For fixed epsilon and for n goes to infinity. Now, this should also be pointed out about the definition of noise sensitive. In the definition, I ask that it should hold for any epsilon, but in fact, we're going to see that it holds for any epsilon if and only if it holds for some specific choice of epsilon. So it suffices to choose, some specific epsilon smaller than 1/2 or something like that. So it really doesn't matter. So let's AK be this probability, which is clearly which is clearly a function of epsilon. But let's not bother about that for now. I want to express AK in terms of AK minus 1. That's what I want to do, basically. So how can it happen that f of omega and f of omega bar are f of omega epsilon are both 1? Well, that can happen if now here I'm going to write the outcome omega. Here I'm going to write the outcome omega epsilon. For example, if there's all pluses there and all pluses there, then of course this is going to happen. And what's the probability of this happening? Well, that's of course AK minus 1 times AK minus 1 times AK minus 1, again by independence. But it can happen in other ways. It can happen that there was all pluses there and only one of them flipped to a minus. What's the probability of that happening? Well, that's 1 over, that's AK minus 1 times AK minus 1 times, yeah, exactly, AK minus 1 squared. And here we have a half, the probability that we have a plus there, times a half minus AK minus 1. Plus, of course, we can also have the same situation that we have a minus there and a plus there. This is going to give us another thing with the same probability. Of course, this minus can in turn be placed in each of these 3 positions or in each of these 3 positions. So in fact, we get a factor 6 here. And then we could, of course, have plus, plus, minus, plus, plus, minus. This is, again, going to happen with that same probability. Or we could have plus, plus, minus, plus, minus, plus. That's going to occur with probability 6 times AK minus 1 times a quarter times a half minus AK minus 1 squared. And maybe that's it. OK, so I went fast there, but I mean, you saw the different essential pattern. And if we write this out, this should hopefully end up being hopefully end up being 4 AK minus 1 cubed minus 3 AK minus 1 squared plus 3 halves AK minus 1. So now we have expressed AK in terms of AK minus 1. And of course, we have a starting point. A0 is just the probability that both this is plus and this is plus. That's going to happen with probability a half times half times 1 minus epsilon. So something slightly smaller than a half. That's the crucial point. So what is this then? What comes out in the end is that AK is going to be the kth power of the polynomial, of this polynomial applied on 1 minus epsilon over 2, where P equals 4x cubed minus 3x squared plus 3 halves x. Okay, now looking at fixed points of this function, you see that when we iterate the polynomial on this input, we're going to strictly decrease. This can be done by some sort of graphical, like looking at the graph of this polynomial. We're going to decrease, and we're going to decrease to a fixed point, and the fixed point of this thing is exactly a quarter. So we're going to converge to a quarter, meaning that this probability that both of them is 1 is going to tend to a quarter, which is the product of the probabilities, which implies noise sensitivity. This is very much rabbit out of the hat, but it's at least not more rabbit out of the hat than using a theorem that we haven't proved yet. So it's your choice. Did you have any questions on that? Then I'll be happy to answer them by the coffee. Thank you.